All right, everyone, let's dive in. Today, we're going to talk about something that is, without a doubt, one of the most important inventions ever. It's a tiny little component that literally powers our entire modern world. We're talking about the bipolar junction transistor, or for short, the BJT. Now, this is a super fundamental topic, so let's really make sure we nail down the key ideas together. But before we get into all the physics and diagrams, let's just think about something for a second. Imagine a concert. How does one person's voice, captured by a tiny microphone, get loud enough to fill an entire stadium? That magic trick is called amplification. It's all about taking a small, weak signal and making it huge. And well, the BJT, that's the little engine that makes it all happen.
So here's our game plan for today. First, we'll get a solid grip on this whole amplifier idea. Then we'll look at how a transistor is actually built. What's inside? After that, we'll use a really simple analogy to understand how it works, check out the main ways to connect it in a circuit, and then I'll wrap it all up with the key facts you absolutely need to know for your exams. Sound good? Let's get to it.
Okay, first things first, what is this thing even for? When you boil it all down, a transistor's main job is to amplify. It takes a small signal and makes it much, much bigger. Simple as that. You know, the name transistor is actually a huge clue about how it works. It's just a mashup of two words, transfer and resistor. Why? Because that's exactly what it does. It transfers an electrical signal from a low resistance part of a circuit to a high resistance part. It's a beautifully simple name once you see what's going on under the hood. So we know its purpose, but what's it actually made of? Let's take a look at how it's put together. You might be surprised at how simple the basic structure really is. At its heart, a BJT is really just a three-layer semiconductor sandwich. Seriously, we take two kinds of materials called N-type and P-type, and we layer them. For what's called an NPN transistor, which you see here, we just sandwich a super thin slice of P-type material between two thicker N-type layers. You can also do it the other way around, making a PNP transistor. But for today, we're going to focus on the NPN, because it's the most common one you'll run into. Okay, now each of these three layers has a wire connected to it, which we call a terminal. And these terminals have very specific names that you just have to memorize. They are the emitter, the base, and the collector. When you see a real transistor with its three little legs sticking out, that's what you're looking at. These names are absolutely fundamental, so make sure you lock them in. All right, so now for the really cool part. How does this little sandwich actually amplify anything? Well, the secret is all about using a tiny little bit of current to control a great big flow of current. The best way to picture this in your head is to think of a simple water faucet, or a valve. Imagine this huge pipe with tons of water ready to flow through it. That's like the current waiting to go from the collector to the emitter. Now, the base, that's like the small handle or knob on the valve. It only takes a tiny little bit of effort, a small base current, to turn that knob. But that small turn unleashes that massive flow of water, the huge collector current. See? A small input controls a massive output. That right there is the core idea of amplification. Now, here's a key point. For this valve to work like an amplifier, you can't just hook it up randomly. We have to apply some specific voltages to get it into the right state to operate correctly. This setup process is called biasing. And our main goal with biasing is to get the transistor into what's known as the active region. That's the sweet spot where it can do its amplification job. Okay, everyone pay close attention to this table. Seriously, this is a classic exam question. So a BJT has two junctions inside it, right? The emitter-based junction and the collector-based junction. To get it into that all-important active region for amplification, you have to do two things. You must forward bias the emitter-based junction, and you have to reverse bias the collector-based junction. The other two modes you see, cutoff and saturation, are basically for using the transistor as a switch, either completely off or completely on. Now, if there is only one equation you burn into your brain for BJTs, it has to be this one, IE equals IB plus IC. All it's saying is that the current coming out of the emitter is just the sum of the current going into the base and the current going into the collector. It's just a direct application of Kirchhoff's current law. It's so simple, but it's the mathematical bedrock for everything we do with these things. Okay, so we know how it's built. We know the basic idea of how it works. So now, let's look at the different ways we can actually connect it into a circuit. We call these different setups configurations. First up, we have the common base configuration, or CB for short. The name says it all, really. The base terminal is the one that's common to or shared by both the input circuit and the output circuit. In this setup, our signal goes in at the emitter, and we take our output from the collector. Next, we have the common emitter, or CE configuration. Now this is the rock star. This is by far the most popular and widely used setup for amplifiers. Here, the emitter is the common terminal. We put our small input signal into the base, and we get our big amplified output from the collector. The reason it's so popular is that it gives us the best bang for our buck. You get a big boost in current and a big boost in voltage. That makes it incredibly versatile. This table right here is your exam cheat sheet. It breaks down the key differences between the configurations. So you see, common emitter gives us high current and voltage gain, which is perfect for stuff like audio amplifiers. Common base, it's great for high-frequency applications. And that third one, common collector, it's a bit of a special case. It doesn't really boost voltage, but look at its resistances. High input, low output. That makes it perfect for something called impedance matching, which is basically acting as a buffer to smoothly connect two different stages of a circuit together without losing signal. Okay, that was a lot of ground to cover, so let's just boil it all down to the absolute essential facts that you've got to remember for your exam. Think of this as the rapid-fire round. Let's go. BJT, bipolar junction transistor. 3 terminals. Emitter, base, collector. Its main job? Amplification. How does it work? Like a current-controlled valve. The golden rule, the one equation to know? Emitter current equals base current plus collector current. And the most popular, most useful configuration? The common emitter. Got it? Good. So let's end with this. We started out talking about a microphone at a concert, but this core idea of amplification is, well, it's everywhere. It's in the Wi-Fi signal your laptop is picking up right now. It's in the sensors in your car. It's in the massive data centers that run the internet. Now that you understand how a BJT works, I want you to look at the technology all around you and ask yourself, where else is this simple, powerful idea of making a small signal huge at play? Thanks for your attention today.